So, last week, both Monday and Wednesday, we were talking about latches and flip flops. Latch, see, latch is a simple circuit which tells you it is possible to put a 0 or a 1 in this hardware, in this circuit, and retain it by adjusting the inputs. For example, in SR flip flop, you put a S is equal to SR latch, you put S is equal to 1, R is equal to 0, output becomes 1, and if you now remove this and make 0 0 as the inputs, then this 1 will continue. Or when you put S is equal to 0, R is equal to 1, it is the other way. That is all, that is called this latch, but it is a sort of a circuit which tells you how to put some bit 1 or 0 into a hardware and keep it. But the problem with the latch is inputs keep changing. So, every time there is a change in input, some of these input changes may be intentional, some of them may be spurious, sporadic. So, we do not want to have this type of uncertainty. We have a flip flop in which we introduce what is known as a clock. Clock is a signal which goes from 0 to 1, back to 0, back to 1, like that, and depending on the frequency, depending on the speed at which you want the circuit to work, you can increase the frequency of the clock. The idea of having a clock is whenever the clock is high, changes in the input will be registered in the flip flop, and whenever the clock is 0, changes in the input will not be registered. So, whatever was the output earlier will continue as long as the clock is 0. And then we also saw clock high can last for a long duration. When you have that, again we may have some, we want only one change to be registered in a clock cycle, whereas when the clock is high, there may be changes in between which may also get registered. So, in order to avoid that, we had what is known as an edge triggered flip flop, where in the positive edge, when the clock goes from 0 to 1, output changes based on the input conditions. In the negative edge triggered flip flop, when the clock changes from 1 to 0, input affects the output, and rest of the time, even though the clock is high, input changes will not change the output. Then we saw several types of flip flops. We started with SR. The problem with SR is a condition S is equal to 1, R is equal to 1 should not be given, because that does not, the prediction, the output prediction is not possible, because it depends on the speed of the two, relative speed of the two NOR gates or NAND gates. So, in order to avoid that, we had D flip flop where the input is always complementary, D and D bar. So, that is a single input flip flop. Output is when the clock is high, whatever you put at D input gets reflected in the output. When the clock is 0, whatever input you had earlier put, that will continue to be there in the output. So, there the question of SR being 1 does not arise, because there S and R are complementary. If S is 0, R is 1, S is 1, R is equal to 0. Then we still had a problem, because that 1 1 condition was not productive. We do not want to have a flip flop in which you cannot have a combination of 1 1 as the input. It may happen accidentally, it may happen in a circuit without your knowledge. So, to eliminate that, we introduced a JK flip flop. A JK flip flop is similar to SR flip flop, except the last row, last condition in S and R are both 1 is permitted, and this is called a toggling mode. It always changes the clock for every clock cycle. the output changes from the previous value, which is 1, to the next value 0, or the other way. So in other words, output complements for every clock period, at every clock period. So these are the 4 flip-flops you saw: SR, D, JK. The fourth one is T, where only the last condition, toggling condition, is given, rest of the things are not there. So when T is 1, output complements itself for every clock cycle, and T is 0, the output remains same for every clock cycle. This is summary, and we wrote the truth tables. We actually call them characteristic tables because they do not, in truth table we are used to combinational logic where we have 0, 1 or do not care as output. Here we have things like as before, memory state and all that are not permitted, all these output conditions. So it is called characteristic. These are the description of the flip-flop. And then we also wrote the equations called characteristic equation. So we saw these things. We talked about, we already told you about edge triggered flip-flops, positive edge and negative edge. And these are used, we will see starting today or maybe next class, how to use these flip-flops, what is the use. Now, before we move on, we also talked about preset and clear conditions. When you want the output to be always 1, irrespective of the input and irrespective of the clock, regardless of the input and regardless of the clock, if you want output to be 1, a signal called preset is given as 0. If preset is 0, output is 1. Clock will not change it, inputs will not change it. Similarly, if you want the output to be 0, regardless of the clock and regardless of the inputs, put as a clear signal. If you make clear is equal to 0, then output is 0, does not change with inputs, does not change with the clock positive or negative, clock high or low. But you should not apply both clear and preset same at the 0 at the same time, because then it is a confusing situation. Okay, what else did we see? So that is a summary of the flip-flops, 2 classes we took. Now a couple of things I have not completed. One is called the master-slave flip-flop. See, we have edge triggered, level triggered, where whenever the clock is high, the output will change based on the inputs. Then we have positive edge triggered, the output will change based on the input. Whenever clock goes from 0 to 1, called positive edge. And we have negative edge triggered, where output changes based on the inputs. Everything is based on inputs when the clock goes from 1 to 0. See, input and the previous output are important, because we have a characteristic table which says as before. What do you mean by as before? Whatever was before this signal was supplied and the clock came, whatever is the output of the flip-flop will continue to be the output. Similarly, toggling means if the previous output is 1, the next output will be 0. The previous output is 0, the next output will be 1. So this is what first class I defined sequential logic. This is what we said. In the combination logic, the inputs determine the output. That's all. In sequential logic, inputs determine the output. In addition to the inputs, we also have to take into account what was the previous output. That is why we have the feedback. So, usually they draw a block diagram like this. Inputs, I will put a one signal. Input, output, this is output, feedback to the input. This is a delay. Because these flip-flops have very little time today, delay time. So, if you do not have this delay, it keeps on going. Very quickly, as soon as the input is given, output changes almost immediately. The delay of this hardware is so small today. So, immediately this will go and change this. It goes on. This is what is called racing. We do not want that. We want to delay it somehow. So, before we change the next input, we delay it and put this so that the output changes every time after a delay. This is sort of a block diagram model of a flip-flop. Okay. Now, there is something called master-slave flip-flop, which is a level trigger flip-flop, but level trigger flip-flop has a problem that whenever the level is high, output will change based on the input. It can happen several times in the clock period. Some of them may be desirable, some of them may be undesirable. We want output to change during based on the input only once during every clock cycle. But we do not want to go for a edge triggered or positive edge or negative edge, in which case we use master slave. Master slave consists of two flip flops. This is without let us say there is a D flip flop, can also work for JK. And the output of the D flip flop is fed to second flip flop D, and this output is final output. So, the input D changes, Q changes. If D is 1, of course the clock is high. If the clock is high, if D changes to 0 to 1, 0, D will be 0, Q will be 0, this 0 will come here, output will be 0. If D is 1, Q will be 1, this will be 1, this will be 1. So, this is same as the one single flip flop, but what is special about it is the clock is given to both the flip flops with the inversion. This flip flop is called a master. This is called slave. So, when input is there, it can be level triggered. You do not have to be positive edge, because positive edge and negative edge, the problem is very difficult to give this triggering circuitry. Triggering circuitry has to be very, very narrow, and sometimes it may be difficult to design it. So, we have a level trigger which is more comfortable. As long as the clock is high, this D will be the output. Now, the clock is high, so the Q will register the input D. But when the D is applied to this D, Q is applied to this D, we have a clock which is not positive, because if this clock is high, this is master clock, slave clock would be opposite, complementary. When this is low, this is high. Because we have an inverter. So you may have an input, it's a level trigger, so the input will change, input will keep changing, but this change will not affect the slave flip-flop. Change will not affect this change, the second flip-flop. Once the clock cycle is over, this is positive, negative. We call it positive and negative. Both are, see, depends on the values. This can be 0 volts, it can be 5 volts, it can be 0 volts, this is 3.3 volts. All signals are positive, maybe also negative. But when you say positive, you mean higher. This is negative. Okay, this way it's called positive edge trigger, going from here to here. Negative edge trigger from here to here, there is no negative voltage involved. It is going down, clock going down, clock going up. So when this is happening, when this has become 0, this clock becomes high. When this clock becomes high, then whatever is the output Q will become the input of D and Q will change. So the final Q will be, after you apply D, it changes here, master changes here, but it will not reflect the output. Then you give the negative here, so this will become 1. So now the slave flip-flop can take this value and show it to the output. So this is equivalent to some sort of a negative edge trigger. Negative edge trigger also the same thing. At the negative edge of the clock, output changes. And one more change, any change here after this, because the clock is low, the clock is originally high, any changes will reflect here. Then this clock became low here and high here. So high clock takes this and goes. But when the input changes, keeps changing, nothing will happen because the clock is disabled, clock is 0. So Q will not change. What was the original value the last time? It will continue. So in a master slave flip-flop, only one change in the output will happen in a clock cycle. And it is similar to edge trigger, positive edge, negative edge trigger. So similar to so whether it is positive edge trigger or negative edge trigger, level trigger has a problem. Many changes in the input happens when the clock is high. Those changes will go to the output, and finally the last change before the clock became 0 would be the one that is registered. It may not be what I want. I might have given the value in the beginning, that value will change the output, but since the clock is going to remain high for a long time, it is going to pick up something else which is happening, and the final output may not be the input that I gave. The same level trigger, if you have an extra flip-flop and a inverter, I will make sure that this change does not affect this because the clock is low, and when after the clock is high, any change here will not affect this. So only one time, even though it is a level triggered flip-flop, master slave is a level triggered flip-flop, but only one input change per clock cycle, and it behaves similar to negative flip-flop. Only one change in output per clock cycle. You can increase the speed of the clock, you can increase the speed, frequency of the clock, and it will also follow. This is the concept of master slave flip-flops. So there are two flip-flops, slightly more hardware, and two flip-flops the delay is more because first flip-flop delay, second flip-flop delay. Two flip-flops, delay is more, hardware is more, but today hardware of flip-flop is nothing, insignificant. It is not a big issue. Delay is also not a big issue because we are talking about picoseconds and femtoseconds, picoseconds at least. So these are not the issues today, even though we may have theoretically compared to a positive edge triggered, this requires twice the number of flip-flops because the hardware complexity and also delays further. All these things is not non-issues today. Okay, this is what I wanted to now say to complete the discussion on flip-flops. There is one other thing. We have been saying when the clock changes, the output changes. Is it really true? Is it ideal? Let us say this. I have a clock. Time delays in flip-flop. Let us say it is a D flip-flop. And D changes exactly at this point from 0 to 1 and remains D for a while. It can fall. It has nothing to do with this flip-flop clock. I am just showing you it happens exactly at this point. And then it changes again here. If it does, we have a problem. It is a positive edge triggered flip-flop. So when the edge is positive, D should appear at the output Q. Q is 0 to start with. So Q will become 1. Let us say it is positive edge triggered. Now, this should happen actually. Q will become 0, then 1, but it will remain 1 for the entire clock period. Once it changes the positive edge, okay, I will put this D a little more later because otherwise it becomes a problem. This is my D. So D remains 1, then becomes 0, again becomes 1 at this point in time for a short while, etc. Now, it should change here from 0 to 1, and it should remain 1 for the entire clock period. This is the clock period. Then because D is not there, it will fall to 0. Again at this positive edge, it will change from 0 to 1 and continue. This is the ideal case. This is an ideal case where we are assuming the clock edge identifies the input and changes the output. But in practice, it is not so. In practice, we have delays. So there are 3 times we have to be familiar with. One is called the setup time, T setup time of flip-flop, T delay of the flip-flop, T hold time. What is that setup time? Setup time is a time before which we should give the input before the clock arrives. Before the clock edge comes, I should leave the input high or whatever, setup times earlier. So, this is not true. This will not come one here. This will not come one here because there is no setup time. At the clock, the input changes. When the clock, the input changes, we are uncertain. It may change, it may not change. So, what we need to do is give the output, input D, a little while earlier. If this is the clock edge, D should change here. It should not change exactly at this point. This period of time between the actual D value and the clock edge is called setup time. The D input should be made available setup time earlier than the clock edge. By factor of setup time, I should have the D ready. So, here also it is wrong. So, I should make it here. So, this is my setup time. So, that is the first thing. So, what is the setup time? Setup time is the time at which the input should change before the clock arrives. If it occurs later than this period, the output is not guaranteed. Change in output is not guaranteed. So, it is at least before the setup time. If setup time is 1 millisecond, 1 microsecond, at the clock edge, 1 microsecond before the clock edge, the output should be, input should be. It can be given much earlier also. It can be given much earlier also. So, this is at least. Setup time is the time by which the input is present at least before the clock edge. Only then this is valid. Now this is valid. What is the delay? Delay is all gates, all circuits have delay. The gate has a delay, inverter has a delay. So, after all, flip-flop is made up of latches, and latches are gates, then we have the input gates. So, this change this time delay, once you give the input, what is the time at which the output can change? That period is called its delay. So, time delay is the time required for the output to change after the input is given, and the clock, of course. When you say input is given, this, even though the input is given before setup time, nothing can happen until the clock comes. So, with reference to this clock, when does the output change? And that is called the delay. That is called the delay. So, that means I should redraw this figure. This is the clock, output will not change here, it will change here. This is my delay. Similarly here, at this point the clock will not change, output will not change, it will change here. Then finally there is a hold time. Hold time is the time for which you should hold the input after the clock edge. So, if the input is here given here, setup time before the clock, I should also hold the output for a little longer. This period is called hold time, T hold. So, again to summarize, setup time is the time at least by which the input should be made available before the clock arrives, clock edge arrives. It can be positive edge triggered or negative edge triggered. Then delay is the time delay is the time it takes for the output to change after the input is given and the clock is applied. It is true of any circuit, even combination logic. Hold time is the time for which the input should be held, should be given, input should continue to be held after the clock edge. That is the hold time. So, now these are three important times you should know. So, what is the maximum frequency at which you can run a flip flop? What is the maximum frequency at which flip flop can work? Because of the setup time, because of the time delay, there is a finite amount of time required for each clock cycle or each cycle of the flip flop. So, this is given by T setup, T flip flop will be T setup plus T delay. So, flip flop can run at a frequency which is inverse of TFF. Maximum frequency of a flip flop is 1 over TFF. So, we give an example of setup time 2 nanoseconds, time delay 3 nanoseconds, T hold 1 nanosecond. My TFF would be 3 plus 2, 5 nanoseconds. T frequency is, maximum frequency of the flip-flop is 1 over 5 nanoseconds, which is 1 over 5 is 20, 1 over 5 nanosecond is 10 power 9 by 5. So, if you take 10 out of this, so 2 in 10 power 8 or 200 megahertz. 200 megahertz. That is very important figure, because when you buy a computer and say it works at gigahertz, the speed of the flip-flop is important. In fact, speed of every component is important. If a component delays the process, the overall delay will be there. So, we have to make sure that we cannot run this flip-flop for more than 200 microseconds. So, if you want faster than this, I should go for a faster flip-flop with less setup time, less delay. Then I can increase the speed. Of course, today this is nothing. Nobody likes to use a 200 megahertz. All of you use computers which are gigahertz. But this is illustrate the concept. So, now we have covered the flip-flop in entirety, starting with latch, and then to make it a flip-flop is a clock latch, then different types SR, D, JK, T. We wrote the characteristic equation for each one of them. We wrote the function table for each one of them. We call it function table or characteristic table rather than truth table. And then we talked about the edge triggering of a flip-flop, edge triggering, I mean level triggering, positive edge triggering, negative edge triggering. We also saw master slave, which is level triggered but works similar to negative edge triggered flip-flop. We also talked about preset and clear. If you want to make output of the flip-flop always 1, you put preset 0 and then nothing will happen. Nothing, any other thing that happens like the inputs and the clock will not affect the output. It will always be 1. Similarly, when you put a clear signal to be 1, 0, the output will be 0 no matter what happens to the clock or the inputs. And you should not make both of them 0 at the same time. Then we talked about timing, important consideration, timing of a flip-flop. We talked about setup time, hold time and delay time. Delay is the time it takes for the flip-flop to change state after the input is given. Input means both the input and the clock edge. Setup time is the time at which, before which you should give the input before the clock edge. Hold time is the time for which you should hold the data after the clock edge. These are the timing, and then these affect the frequency. The overall delay of flip-flop is setup plus delay time, and adding them you get the F max is 1 over TFF, and in this example we have 200 megahertz. Do you have any questions on the flip-flops? Kannan, can you unmute them? If somebody has a question, raise your hand. Raise your hand, except I am raising my own hand, I can see that. If any of you has questions? Anybody has questions? In the last 2 lectures, actually 2.5 lectures. Okay, no questions, good. So, we will change gears a little bit. I am going to start the next topic of counters, but not today. I thought I will work out some problems in assignment, some problems today, from what we have covered earlier. Let us work out a couple of problems. One. Implement the following Boolean function using four to one multiplexers. Oh my. F of ABCD is sigma m four 6 9 12 14. Please work out the problem, and we have a solution. Raise your hand. Do you understand me, all of you? Anybody? Work out the problem. When somebody has a answer for this question, raise your hand, I will unmute you. I want them to give some time for them to work. If you unmute them, there will be only marketplace. Kongu, are you hearing me? No, you just wave your hand. If you are working on it, wave your hand. That's enough.
Yes, sir.
Yeah, okay.
Yes,
they're both doing it. Take 2 minutes and come up with a solution. If somebody has a solution, wave your hand. Okay, anyone with a solution? What, man? A very simple problem I have given. I have taught this so much. Multiplexers and all that, and Boolean algebra, reduction, corner map. Not a single soul. That depresses me. One of the simplest problems there is. Next problem is going to be more complicated. If you can't do this problem, I think I need. Okay. In the interest of time, I will do this. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Huh? Good. Give me the solution. Yes. Who is this?
4 to 1 mark.
Who is it?
IRTT.
Ah, very good. Tell me.
Sir, 4 to 1 mark state.
Yeah,
And
that's what
AB is
Dinesh,
the
sir.
character encode.
That is Dinesh.
Slowly, talk slowly, man. 4 to 1 marks. Okay.
AB is the selector encode.
A? A, B.
B is the selector input.
Okay, AB is
Yes,
selected
yes.
input. Okay, then
First one is D bar plus C bar.
what? C bar plus D bar. Okay,
Yeah.
tell me.
Second is D bar.
D bar.
Yes.
Third one.
Third is D. Yeah. Third
Third
is
is
exclusive or D.
what? Third is what?
Third is C exclusive or D.
Okay, I'll have to verify this. I'll just write what you say now. Okay, four. What is four?
CD. CD.
CD.
C and D.
C and D. Okay. Thank you. Let me verify this and see. I've already started doing it here. See, when the AB is the selector, we have to choose these two. That is, we have two variables here. As it says, it is D bar, C bar. So this is right. Second one is a D bar. D bar, D bar. That is the second one. A bar B is the selector. Third selector is AB bar, the last row. AB bar, in my opinion, it should be C bar D. Why do you get exclusive or CD? I'll come to that. The fourth one is this. This is C bar. Fourth one is D bar. This is same as this. So this is wrong. This is D bar. This is wrong. This is C bar D. The person who answered, can you see the difference between my solution and your solution? Who is that guy? The person who answered me. What's your name? What is your,
Dinesh.
huh?
Sir, Dinesh, sir, Dinesh.
Dinesh, do you see the solution I have written? Do you agree with me?
Oh, yes, sir. Yes, sir. 1 minute. I have check that.
Okay, if I made a mistake, you have to point out. Right now, I think it is right. Anyway, thanks for trying and thanks for getting half of it right. Okay. Okay. This is F. Now I am going to give you a second problem as example. Suppose I have delays T OR gate is R, T AND gate is N, no D, T inverter N and T exclusive R X. So four types of gates: AND gates, OR gates, NOT gates and XOR gates. You can also put some numerical numbers. They just called it R, D, N and X, it doesn't matter. Now, there are two parts to this question. What is the delay of the final sum in a 4-bit ripple carry adder? 4-bit ripple carry adder has how many outputs? Depends on A0, B0, A0, A1, A2, A3 and B3, B2, B2, B0. So the last sum is, this is first sum, S0, S1, S2, S3. 4-bit ripple carry adder, delay time of S3. That means it has to go through 4 full adders. So the ripple carry adder we talked about in class. First bit goes to the second bit along with the carry, second bit along with the carry goes to the third bit, etc. What will be the time delay of this 4-bit adder for the last output, The second part of the question, let me first get the first part right. Then the second part of the question is compare it with the time delay of S3 for a carry required adder. We saw all these things, nothing new, it's a revision. Is there any question on the question? We first understand the question. If somebody is not able to understand the question, please raise your hand. Is the question clear? Then start working on the answer, first part at least. Yeah.
We couldn't see the question, so can you just read it for us?
Oh, there are 4 types of gates: OR gate, AND gate, NOT gate, exclusive OR gate. Okay? OR gate, let us assume the delay to be R, small r. AND gate, we will assume the delay to be N. D. NOT gate, we will assume the delay to be N. Exclusive OR gate, we will assume the delay to be X. There are 4 gates. This only R means R. And so we put a D. Not so put a N. XR means X. Now, you know 4-bit ripple carry adder. You have four stages. The ripple has to go from first stage to second stage, second to third, third to fourth. So I want you to find out how much time it takes for the final output. S3 is the last output. Because I have A0, A1, A2, A3. Sorry, B0, B1, B2, B3, and results in S3, S2, S1. What is the time it takes to get S3? Anyone?
Aruna, you're also unmuted. Please go ahead.
I don't know.
Dinesh, you're also unmuted. Manikantan from Alpha, you're also unmuted. Professor is asking a question.
Somebody give me the answer first. தண்ணி ஊற்றப்படுது அதாச்சு டஸ்ட்டு. ಅಮ್ಮ ಬಂದ್ಬಿಟ್ಟಪ್ಪ. This is full adder circuit. Come on, somebody has to come up. Very simple problem. Nappa. See, first bit, second bit, third bit, fourth bit. A, B, I. You see, I have done all this. Again and again I can't be doing. So sum comes out here, S0, S1, S2, S3. Carry, input carry is 0. So Z0, Z minus 1 is 0. Then becomes Z0, goes to this, comes out as Z1, goes to C2, and comes out as C3. What is the carry delay time? Carry is a simple circuit. 3 AND gates in parallel. AND gate delay is D. D, D, D. OR gate delay is R. D plus R. D plus R is the delay for the carry. Now this D plus R goes here, starts this, another D plus R. So this is 1C, 1, 2, 1, 2, 3. So this is, because the final output can come only after C2 is given, which is 3 times Ci delay, which means it is 3 times D plus R. Now, add. See, here the sum has to be taken into account. Sum has 2 exclusive R's. So this is X, this is X. After Ci comes, it takes 2XR to 2X. So after this, I need 2X plus 2X. So delay is 3D plus R plus 2X. So if you put values, this is the time delay for S3. This is how you do it. You find out the delay of carry. These are parallel gates. You don't have to add them. One and all this one AND gate, one OR gate in the path. This is D plus R. So D plus R is the time it takes for the carry to be generated. Now this D plus R has to go into this, another D plus R. This has to go into this, another D plus R, and this has to go into this, another 3 plus R. So 3 times D plus R is required before C2. The final S3 can come only after C2 is given. So that is going to take 3D plus R. After that what happens? AI, BI, CI. So, this is going to be 1 XR, this is going to be 1 XR. So, after the carry is given, it is going to take 2 XR delays for the sum to be generated. So, this plus this is the total time required for computing the S3 of a carry, ripple carry. When that is the case for you, nobody has come forward. How am I going to work for the carry look ahead adders? We talked about carry look ahead, if you remember. So, I will give it as an exercise. Do the same problem for the 4th bit output, that is S3. If the adder is not a ripple adder, but it is a carry look ahead adder. So, repeat the problem for this. Again find S3 for carry look ahead. Do you think it will be less or more? At least you can say that. Carry look ahead time is more or less? Come on, somebody answer me. Hey, carry look ahead completely covered, I say. Is carry look ahead adder delay time is more than ripple adder or less than ripple carry adder? Not even a single person can answer this question. Yes, what is that? Tell me.
Is obviously less, sir.
Obviously less, but obvious you are not working. It is obvious to you, but you have to give me the value. Yeah, you are right. It is less. Do you know how to do this same problem for carry look ahead? Hello? You know? Okay, do it at home. Okay. I'll work out one more problem. This one I'm not doing the second part because even this nobody came forward with the answer. So the other one is somewhat little more complicated. I don't want to go through it without anybody contributing. The idea of this question answer session is for you to tell me how much you have learned. The idea of question answer session is for me to find out how much you are able to understand what I am saying, how much you are able to grasp what I am saying. If you are going to be sitting like this for every question I am asking, then it's very difficult for me to gauge. Is the lectures going useless? Or are you learning and not come prepared? What is the reason? Please, whenever I ask you a question, at least part of the answer you can. For example, the other guy gave me the problem for multiplexer. Maybe one or two things were wrong, but at least he knows how to do it. Now you are saying obviously it is not small. Yes, you are right. But you will have to tell me how. Okay. One more problem. The last of the 3 examples I wanted to do today. See, carry is given as in full ripple carry adder or AI, BI, AI, CI, BI, CI. We have seen this. We have drawn the circuit, we have done the corner map, everything. Now, can you reduce this to GI, PI, GI bar, PI bar, CI bar, CI bar, whole bar, what is GI? From triple carry adder you should know, from carry required adder you should know, GI is nothing but AI, BI. PI is nothing but A exclusive or BI. Oh, the question is a very simple, again a very simple question. In my mind everything is simple, but this equation all of you know from full adder. Even before I taught it, you must have known it. Next stage carry is given as the present inputs A and B, present input A times the present carry, present input B times and the present carry. This equation can be reduced to this form because sometimes it is useful to have this type of different versions for implementation purposes. We have two functions we defined earlier. This is called propagation, this is called generate. Carry generate, carry propagate. We saw these terms in connection with carry required adder. This is GI is AA, BI, PA is AA exclusive or BI. This is a simple exercise of rewriting this and fitting it to this. You have to do some manipulation on this because it's negative. So you have to do it such that this comes this. It's something like a bookwork, something like a derivation. There is no concepts involved here. Now we will take this GI, PI, GI, CI means I can take a demarcate it and write it as GI and PI or GI or PI and GI or CI. All you have to do is to multiply this and match to this. When you multiply this, GI times GI is GI, GI times PI, CI GI, PI GI, CI. Now you substitute now the values of this to this equation. You substitute A, B for G and A exclusive or B. Then you simplify it, you will get this. Boolean algebra. Not even Boolean algebra. Simply multiply, expand, identify this has to be this. That is all. Okay, I am stopping here today. Next lecture I will take on counters. See, there are two things I am assuming. All of you please note. Number one is that you have gone through my I am expecting you to come see, I am following NPTEL lectures closely, and I also given you the handout in the beginning. It is in the website also. The coverage of this material and what are the relevant NPTEL lectures for each lecture. So, I am expecting you to go through these NPTEL lectures before you come to the class for that particular day. Each day what NPTEL lecture will be covered is given in the syllabus in the website, number 1. So, that is one. First requirement is please come prepared with those NPTEL lectures so that my job becomes simpler. Like this I can do problems. More of these problems I can do if you are familiar with the material already. Second thing is, when I ask you something, if you do not respond, I have no idea how much of it has gone into you. See, I am assuming you are understanding and grasping what I am teaching. So, even for simple questions you do not answer, is it because you do not know the answer, or is it because you are afraid, or is it because you have the answer but you are hesitant to do it? If nobody understands anything and nobody comes forward to give answers even for simple things like this, that multiplexer problem, except that guy, and this, what am I supposed to assume? Am I supposed to assume that nothing goes through? So, please think about these things. You have to take this seriously. Any class you have to take seriously, whether it is Aruna Engineering College class, Kongu Engineering College class, or private person. Whenever you start doing some work, you have to take it seriously. So, if you take a little bit, if you put a little bit, see, it is a very simple material, the NPTEL is already there. All you have to do is go over it. And if when you go over it, it becomes so simple, you do not have to completely see it also. You can quickly browse through it. Then come prepared. And then these simple questions, I have done CLA. I have spent a lot of time on CLA. I have done this. I have done this. And I have done this, delays. Please, that is my request to you. We will see you on Wednesday and we will talk about counters.